Hello, my name is Elizabeth Sampley, and the issue that I'm going to talk about is nuclear waste. So first, I want to go over some of the background. The United States has 98 operating nuclear reactors. 19 of those are in the process of decommissioning, so that means retiring the facilities and disposing of the wastes that were generated during operation. The problem is that we have only one long-term storage facility. That is the Waste Isolation Pilot Plant located in New Mexico. It has the storage capacity to hold 175,570 cubic meters of nuclear waste. The federal government has slotted that facility to accept 15,000 cubic meters of excess waste over its storage capacity in the next, I believe, within the next decade. So as of right now, we don't have anywhere to put that high-level nuclear waste. And the way that waste is sort of categorized in terms of waste deposition, 96% of it, specifically for the Waste Isolation Pilot Plant, is contact handled, meaning it's low-level waste that can be touched and transferred by humans. The remaining 4% of that is high-level waste that needs to be transferred and deposited using machinery because it's too hazardous for human contact. And the picture to the right, is just a schematic showing the current Waste Isolation Pilot Plant in New Mexico. It shows the ground level storage facility and separation facility, and then the 600-meter depth long-term depository. And the way this works is that low-level nuclear wastes are packaged up and stacked on top of each other. Eventually, the salt deposit that these are placed underneath will compress and sort of concrete that stack so that it is permanently located there. The high-level waste is placed in specialized storage containers that are made of concrete or steel, and those are bored into the existing rock. This site was specifically chosen due to the geological rock deposits that have low porosity and low permeability. This is a map of the United States that shows all the different points where nuclear waste is generated and the travel routes those sources take to reach their final destinations. As you can see, there are only 2 nuclear dump sites. These are the long-term repositories, one of which is the repository, the Waste Isolation Pilot Plant in New Mexico, and the other one is not currently finished, but it's the Yucca Mountain proposed site in Nevada. So every bit of nuclear waste that is generated by the Department of Energy eventually will make its way to the Waste Isolation Pilot Plant. So just looking at this map, you can see how much of it we generate and the need for additional sites. So why is nuclear waste dangerous? This is something that I think there exists a pretty large misconception about. People often conflate contamination with radiation, and they're 2 separate things. In my experience as a radiation worker, I was explained the difference this way, that contamination is the garbage and radiation is the smell. But both can be bad for different reasons. So according to the Nuclear Regulatory Commission, contamination is undesirable radioactive material with a potentially harmful effect that is either airborne or deposited in a concentration that may harm people, equipment, or the environment. And the radiation that we should be concerned with is ionizing radiation. And that is energy given off by matter, which may cause changes in living cells. And the way that this kind of radiation is classified, sort of in 3 tiers based on the biological damage that it could cause. So tier 1 is low-level radiation. If you're exposed to that, your cells will repair themselves and there will be no long-lasting damage. For intermediate types of radiation, still within maybe the normal range, cells could die and be replaced. And I think this is something that happens normally, naturally, on a daily basis, so it's nothing really to worry about. But the 3rd level is something that could be dangerous. That would occur for high-level radiation exposure, and in that case, cells incorrectly repair themselves, resulting in biophysical change. So this is where cancer risk comes into play. Okay, so cancer risk. Often when we talk about nuclear radiation, we link that to the risk of cancer. And looking into this, there's not a lot of concrete data that backs that up for low doses over long periods. That would be the kind of exposure that you would get possibly by living close to nuclear waste repository or as a rad worker working in a nuclear power plant. So the cutoff for high dose is greater than 50,000 millirem in one instance, and that causes acute radiation syndrome. That's the sort of, I don't know if anybody's seen the Chernobyl documentary on Netflix, but that's the kind of radiation sickness that was depicted there that causes instantaneous symptoms, painful experience, and death within a really short amount of time. Compared to that, radiation worker exposure is regulated to less than 5,000 millirem per year, and that may still sound high, but so far as the current data shows, the link for increased health risks, specifically cancer risk, less than 10,000 millirem, is inconclusive. So that's a pretty conservative dosage. And then I think it's important for everybody to be aware that annually we receive about 620 millirem just based on coming from natural sources and from like industrial and medical sources. So these are things that we can't really keep away from, but that we are receiving every year. The Hanford nuclear site came up a lot in my research. It's called the most toxic place to live in America right now, based on the unplanned release of radioactive materials from the site. It was initially a nuclear weapons production site. It opened during World War II and was responsible for creating Fat Man, which was later dropped on Nagasaki, and responsible for killing 280,000 people, all told. There have been a variety of studies that came out of the Hanford nuclear site based on reported health risks from workers at the site. So there's a study that took place between 1944 and 1978 that revealed an increased risk of death from lung cancer and tissue cancer. Those are associated with exposure to plutonium, which was being reprocessed at this plant. Also, there have been some health hazard concerns related to groundwater contamination. The way that low-level wastes were stored at Hanford in the 1940s gave rise to the release of radioactive materials into the groundwater, which later spread to the Columbia River. And this became a huge public health scare, although nobody is really sure how the release of radioactive material into a well-used water source would affect populations in the area and then downstream. Okay, in light of research that shows that we need an additional nuclear waste storage facility, I have two objectives. So the first objective is pretty obvious, and that's that we need a new long-term storage facility. And the design criteria are listed here below. It needs to be sustainable over the lifetime of radioactive or radioisotope decay. The number that's usually cited is 10,000 years. So whatever storage casks or containers need to be hold their integrity for 10,000 years. According to the Nuclear Regulatory Commission policies, the facility needs to be safe and environmentally acceptable based on thorough risk assessments. And this is something that the second proposed waste deposit site has been criticized for not having thorough risk assessments. So after that, the proposed facility needs to promote public confidence, sort of with a combination of environmental risk assessments and public relations between the Department of Energy, which oversees the construction and licensing of waste repositories, and public organizations or state and local governments. And then finally, the storage facility needs to be cost effective. Objective 2 includes more of a technical solution to nuclear waste reduction, and that is to reuse and recycle fuel materials. This is something that the United States sort of gave up on in the 1960s, but other countries have made more progress on. For instance, France recycles a lot of their used uranium and plutonium fuels by keeping those fuels separate and then reusing them in a mixed oxide facility. And I'm not sure exactly how that works, and I don't want to go into a lot of technical details about it, but they gain 25 to 30% more efficiency from their reactors. So the design criteria for achieving Objective 2 would include reducing the amount of high-level radioactive material through recycling, increasing nuclear power plant efficiencies, and as with Objective 1, this would also promote public confidence and be cost effective. So the main solution that I want to talk about pertains to Objective 1, and that is long-term storage, specifically deep geological repositories. The United States has a proposed second deep geological repository. It's Yucca Mountain in Nevada. That was chosen in 1987 by Congress. There was a lot of research that went into choosing the site. There were, I think, 4 or 5 sites that were being considered at the time, and Yucca Mountain was eventually chosen based on its geological characteristics, its separation from the public, it's out in the middle of nowhere, and